So in the last video, we worked a few, we learned about the area model to represent quadratics, and we used these tiles to represent, for example, this quadratic, 1x squared, 6x's, and 9 units. And we realized that if we can factor a quadratic, we can also lay these tiles out in a nice rectangle, or in this case, a square. And the dimensions of the larger square are the factors of this quadratic. And not every quadratic can be factored, like this one, for example, x squared plus 2x plus 12. Here I've represented it with this collection of tiles, but maybe you already noticed that there are no two numbers that multiply to make 12, but add to make 2. So there's no real way of arranging these tiles into a nice rectangle. But that's where completing the square comes in. And um, today we're just learning about how to take a quadratic like this and rewrite it um, using this method called completing the square. We're actually going to use that strategy to solve quadratics as well. And there's a couple other important applications that have to do with um, when we graph quadratic functions, and also when we start learning about the equations of circles. This completing the square is a very useful technique. So what I'm going to do is just take my two x's and I'm going to divide them evenly on these two sides of my x squared tile. And then what I'm trying to do is actually make a perfect square. And the first step is just to take my x squared, put it in the top left corner, take these two x's and divide them up between these two sides. And then notice I'm missing one tile right here. I could fit just one of these guys right here. So if I put that into place, this becomes a perfect square with these dimensions, x plus 1 by x plus 1. And then I have these 11 tiles left over. So I could actually rewrite this expression like this. And notice it's a perfect square, x squared plus 2x plus 1. That's this thing. And then I have to add in the 11 additional units to get to 12. So notice these two expressions are equivalent. And you also might notice that one way to check and see if you properly completed the square was, first of all, make sure that you have a perfect square term and a constant term. Otherwise, you haven't completed the square. But if you have those, you can multiply back out this perfect square and then combine any like terms to make sure that you get the quadratic expression that you started with. So we're going to take another example here. Now notice this quadratic can actually be factored as x plus 3 times x plus 1. But and maybe you see something like this and you're like, oh, I know how to factor that. But take a look. We're completing the square right now. We're not factoring. So let's keep that in mind um, as we move forward with this problem. But first of all, I just represent my my quadratic expression with this collection of tiles, and then I can rearrange them in this way. Now, again, you'll notice I could take this x right here and put it down here. And I could take this unit and also put it down here, and then I would have a perfect rectangle whose dimensions are x plus 1 by x plus 3. But again, we're not factoring this thing. We're trying to complete the square. So what I have to do is take my x squared and then divide these four x's evenly between here and here. And that gives me the dimensions x plus 2 times x plus 2. And then I take my three remaining tiles, I put them here in the corner, but I'm missing one. I got to complete this square by adding 1. But I can't just add 1 to my expression. Uh, that changes the expression, so I have to be clever. And if after I add 1, I subtract 1, what I've really done is I've added 0. So this is a clever use of the addition property, the identity property of addition. So I just added 0 to my expression by first adding 1 and then subtracting 1. And now I have a perfect square with these dimensions. As long as I subtract 1 from that, I, uh, I haven't changed my expression. It's still equal to my original expression. And you can see that if you multiply this out, you get x squared plus 4x plus 4. And then if you subtract 1, you get your 3. So that's how we complete the square. And a couple things. You might have noticed that all of our uh, quadratic expressions so far have positive terms. And even like completing the square, notice I was able to take this 4x right here and evenly divide it between these two places because 4 is divisible by 2. But we can handle negative terms and terms that are not even. Um, and I'm going to do that here on the next slide. Notice this expression has a negative middle term. And while, the idea of negative area is kind of a complicated one, so instead of trying to use individual tiles to represent this negative term, I'm just going to go back to my generic rectangle and just remind you that the x squareds always go here in the corner. And so this little corner has dimensions x by x. And then I'm going to take my negative 6x and divide it evenly between these two boxes. And when I do that, maybe you can already see that if you want this thing to be a perfect square, it has to have these dimensions. This x times this negative 3 gives me this negative 3x. And this x times this negative 3 gives me this one. And so I have to have a 9 in this corner right here. Negative 3 times negative 3 makes 9. So that's a perfect square. But I have 13. So in order to get 13 units out of this diagram, I have to add an additional 4 to this thing. And so when I actually write this out in its factored form, or let me say, what I really just did was I took my 13 and I divided it between these two constant terms. One of them is the 9 in order to complete the square, and then there's 4 left over. So when I factor, I get an x minus 3 squared, and I still got my plus 4 hanging out on the outside. So that's how you complete the square when you have a negative term. It's really the same for when uh, that middle term is positive. Um, Now, if we have an odd middle term, again, it works in the same way. We just get a little complicated because we introduce a decimal in this case. My top left corner, of course, is x squared. And then I take my 5x's and I divide them evenly between the two corners. And you'll notice that you can already figure out what the factors are going to be for this perfect square. It's going to be x plus 2.5 times x plus 2.5. And which means that this bottom corner has to be the product of 2.5 and 2.5, which is 6.25. But I don't have 6.25, I just have 5, right? So if I put a 6.25 here, I need to subtract off 1.25 so that the combination of these two together make my 5. And once again, what I really did was I just, in a very clever way, figured out how to split my 5 into two constant terms. One of them completes the square, and the other one is meant to just get me back to the original expression. So when I factor my perfect square, I get this, and then I still have to subtract off the 1.25 in order to make sure that it equals the original expression. So here you have um, 5 problems that you can work out. The task is to complete the square. So once you do that, you can, if you pause the video right now and work those problems, and then when you come back, you can look at the solutions. Also, there's a hint about how to get started on this last one here, and the solutions are coming now.